No, it's just a fancy word for stirring, breaking up. Clumpy solid, break it up. Break it up. With your spatula. Okay. Let's finish up this handout, and then we have another one on reactions. Another white one. Final three compounds here shown, heterocycles. They're obviously heterocycles because they're cyclic and they have a heteroatom, but are they aromatic or not? Or anti-aromatic? Furan. Well, oxygen has two lone pairs. What do we get for furan? Aromatic, anti-aromatic, or non?
Aromatic.
Why is it aromatic?
It has
4 and plus 2.
6 pi electrons.
It has 6 pi electrons, yes. I'll draw this sideways here. We can show the oxygen. Oxygen has two lone pairs. What's the hybridization of the oxygen?
SP2.
Yeah, SP2.
One electron makes pi bond, one electron makes pi bond. And then the oxygen is sp2. Trigonoplanar. The three lines are trigonoplanar. Bond, bond, lone pair. And perpendicular to that is p orbital. We're going to put a lone pair in the p orbital. And now we have a cyclic conjugated system with 1, 2, 3, 4, 5, 6. 6 pi electrons. If we graph this, it's sp2. Gives us this setup. Sigma bond to carbon, lone pair. Lone pair has to be here because it doesn't have to be there. I'm sorry, we got two lone pairs. I was thinking we need to put a pi bond here. There is no pi bond shown. There's two lone pairs. We see two sigma bonds. Then the lone pairs have to be here and here. Lone pair to p orbital. The other lone pair is a hybrid. This is trigonoplanar, right? Trigonoplanar being like that. That's the three lines here. The oxygen, bond, bond, lone pair. Of course, the lone pair is an orbital. Of course, all these are orbitals. Trigonoplanar. But this orbital is interacting with another orbital, interacting with another orbital. That orbital is not interacting with anything. It's just holding two electrons. We call that a lone pair. But it still demands a region of the space. Right? Same old thing. That's organic 1. Organic chemistry builds. We build towards understanding this structure from day 1 of organic 1. So yes, it's aromatic. It's 6 pi electrons. Furan, commonly found ring. I don't see it in a lot of drugs. Nitrofurantoin, got furan in the name. Nitrofurantoin, I think, is an antibiotic that has a furan ring. General Mills used to be the biggest producer of furan, or one of the biggest producers, in addition to Captain Crunch and whatever else they make, because furan can be made from the leftover corn that doesn't make it into cereal, because corn has lots of sugars in it. And 5-carbon sugars can be dehydrated to furan. Well, when it's originally, you get the aldehyde. That compound there can be made from 5-carbon sugars through a dehydration reaction and cyclization. Okay? But then you can remove the carbonyl group, remove carbon monoxide, and have the H bonded here instead, and you can eliminate one of the carbons, and you can turn your corn into furan, and you can make some money on the side while you're selling Captain Crunch and what else do they make? Cocoa Puffs or something. Diaphene, what's the difference?
Nothing.
Well, what was that?
I said nothing.
Okay, that's close. Sulfur right below oxygen, same bonding. Just like oxygen, one lone pair is in a p orbital to make it aromatic, and the other lone pair is in a hybrid. What is the difference? What are some differences though?
It might be more reactive. Yeah.
Do it.
It might be more reactive.
Diaphene might be more reactive. What do you mean by more reactive? More reactive towards what?
I'm saying that perhaps an alcohol can attach the sodium, the sulfur.
An alcohol could attack
I
the
was saying I could be more reactive because it can form more bonds than
It's larger, so it can handle charge better.
Let's get to that. What do you mean it's
it could be more reactive like this look like you were saying.
No, I think what you might be getting at, maybe you're wrong, is because sulfur can expand its octet,
Yes, sir. That's what I was trying to.
and you could have other bonds to that sulfur.
Yes, sir.
Okay, that chemistry is possible. In fact, you can oxidize the sulfur and you can make that. And then we can ask, is that aromatic?
Yes. Those of resin.
That's called a sulfone, when you have SO2. Is that aromatic?
Wait.
I guess it's no.
Okay, gotta be very careful. That sulfur doesn't have a lone pair. There's no lone pair there, right?
Okay, yeah.
Not aromatic. There's no lone pair there. Something to think about. We started by saying there's two lone pairs here. How do you know that?
Standard bonding for oxygen.
Okay. First point here is to, okay, can you know if there's a lone pair there? We didn't even think about it because we know oxygen standard bonding has two bonds, two lone pairs. But sometimes we have to think about it. For example, over there, how many lone pairs on the boron?
0.
0. So, what is it? Is it aromatic, anti-aromatic, or non-aromatic?
Non-aromatic.
Or
Anti-aromatic.
It's anti-aromatic.
Because, okay.
These are aromatic, very common heterocycles. Before we get to that, and by the way, there's another difference here. When we drew this p orbital here, and maybe someone said it, what's the difference in this p orbital? Okay? If this is sulfur, what's the difference in the p orbital?
Larger.
It's larger. Because we're dealing with not a 2p, but a 3p. And each level you go up, the orbitals get bigger. So the sulfur here, I'll try to draw it right here, acting as if it's right here instead. The sulfur p orbital is much bigger. Okay? What does that do to our structural considerations here? We don't often talk about size of orbitals or how that influences things. How's that going to influence the conjugation, the orbital overlap?
Is it going to reach farther? Or
The orbital overlap is not as good. Because you got all this electron density spread out, and you're trying to make it effectively overlap in a smaller region. The oxygen orbital interacts better because it's the same size. I mean, it's like here, these two can come together. Both some amount of electron density here spread out this much, they can come together. What if I don't have anything, long enough. What if we spread the electron density out like this? And it's like, hold on, you can only interact here. This electron density is not able to interact because it's more spread out. So orbital orbital size is important. There's less conjugation here. How do you know that? Well, you can do things like NMR and stuff and other things, and you can determine. Okay? Yes, they're both aromatic, but like I said before, there's degrees of aromaticity. How much, etc. That's bad for this. There's actually something bad for this, because for this to be fully delocalized, this oxygen has to let these electrons fully come delocalized. Oxygen doesn't like to let go of its electrons. It likes to hold on to them. So oxygen doesn't delocalize as much. But it has a better orbital for it. And so these things sort of balance each other out. I think thiophene is going to be more aromatic. Mainly because oxygen doesn't like to let go of its electrons. It doesn't like to fully share, get the full delocalization that is powerful for so-called resonance. Okay, boron. There's no lone pair there. We do have p orbital, p orbital, p orbital, p orbital, one electron, one electron, one electron, one electron. Pi bonds, what's here?
An empty orbital?
This boron is sp2. And it's got an empty p orbital. It's cyclic conjugated. You got 5 p orbitals there, all conjugated. How many electrons in the pi system?
4.
4 pi electrons. Anti-aromatic. If planar. You never see that compound anywhere. I don't even know if it's a known compound. It may be so unstable that it's not even known to exist. It might be just a theoretical. I don't know much about it. It's certainly not aromatic. Very likely anti-aromatic. Making sense? Of course, you got to know chemical structure and periodic table of boron. But hopefully that began in Gen Chem 1, right? And so you know how many electrons are there. And now we know in Gen Chem and Organic 1, we know hybridization that we expect. And now we're building upon that to ask, well, how about aromaticity? Okay, so our knowledge is building. Anti-aromatic. Is that it for this handout?
Yes.
Questions about aromaticity? Should be lots of questions in your textbook. The white handout. Nomenclature. How are we doing with nomenclature? How's the nomenclature video look? Okay, reactions of aromatics. Lots there. Good chemistry. Very important. To be your most common chemistry is, one of them is aromatic chemistry. Super common, super important. The other is substitution reactions, like SN2. I mean, it's very ubiquitous. All right? So reactions of aromatics, there's some warm up there on the purple, including our outline. We see a diagram of the reactions we'll be doing to put substituents on the ring. Starting with benzene, okay? I drew an H in here because we're going to replace that H with a substituent. All right? Do substitution reactions. But the H is not a leaving group. Is H a leaving group? Well, is a substitution reaction, but it's not a traditional leaving group. That's because it's an electrophilic reaction, not a nucleophilic reaction. Right? Yes, it left. I reckon you can call it a leaving group, but it's not really a leaving group in our classical definition, like SN1 and SN2. No. It's a substitution reaction there because we are replacing the H. All right, we'll do nitration, which you're doing this week in lab. Anybody ever nitrated anything? Some of you have already. Okay? And get a nitro. We'll see the nitro can be reduced to the amino. And these two steps are our first two steps of the 8-week lab. We'll be using fluorine as the ring system. Not benzene. Benzene's a liquid. Fluorine is a solid that we're using. We'll see a miscellaneous reaction where the amino group can be substituted with various things called a Sandmeyer reaction. But back over here, we can replace the H with other things. We can make sulfonic acids. We can replace the H with halogen, which you actually did last week. You did it with sulfanilamide. Replaced H's with halogens. That's what we did last week. You can also do a substitution and put a carbon group on the ring. Carbon group. You can also put a carbonyl. And we'll see that the carbonyl can be reduced. It's almost like you're losing a carbon here. We're not. It's going to be CH2R. But CH2R is just a longer form of an R. One extra carbon. So we'll see all this chemistry. This falls under EAS. These are all electrophilic aromatic substitutions here. That's not an EAS. That's just something we do there. Mechanisms for this chemistry. There's 3 mechanisms we will see. The first is called electrophilic aromatic substitution, EAS. That's where we will begin. Here the ring reacts with an electrophile. The electrophile is the reacting thing. That's why it's called an EAS. We'll also and we'll spend a lot of time on EAS. It's the most common. Okay. We'll also then look at NAS. Here the ring reacts with a nucleophile. And when we do NAS, we'll have traditional leaving groups on the ring. Like we'll substitute a bromine with something else. But in EAS, we're substituting an H usually. Nowadays. So 98% of the time, we have to be aware that 2% we can do the same thing. We'll also see the benzyne mechanism, which actually kind of begins with an E2 elimination. Okay. First though, EAS. Question?
I was just wondering, if you have on the benzene ring a methyl, and then you have electrons attack a electrophile, as it travels, as that carbocation is delocalized around the benzene ring, can it be stabilized at that methyl, and then the methyl be a leaving group instead of the H? I have a diagram
Just
of it.
be careful about calling them leaving groups.
Yes.
I'd rather you refer to a leaving group as more of the classical, like SN2. And when we did that, we had requirements for leaving groups.
Yes.
I'd rather you stick with that. Terminology goes with those requirements.
Okay.
Yes, the H does leave, as we said. But I'd rather not call it a leaving group because then you're going to get it confused with... So just be careful about that.
Yes, so I wasn't referring to the H as a leaving group. I was trying to avoid the H being a leaving group.
Well, then you said methyl is a leaving group.
Yes, sir.
But again, we would never have a methyl be a leaving group in SN2.
Okay.
Just be careful about using that leaving group term.
Yes.
Because to me, whenever you say leaving group, we have restrictions there for SN2.
Okay.
And So if you know what you're talking about, you know what you're doing, fine. But I just try to keep you out of trouble because you can start confusing your knowledge.
Okay.
Leaving group requirements. SN2, SN1. Here, everything's kind of reversed because it's an electrophilic reaction. When you do an SN2, and you replace this, what do you react it with? Something like a Williamson ether. You generate this, and then you come in here and you kick off the leaving group. But what is this thing reacting with? What do you call this? Nucleophile. But in EAS, we don't react it with a nucleophile. We react it with an electrophile. So it's the opposite. And so you're going to have opposite things going on, and you're going to get confused, I think, until you really master the material then. Okay? Be careful about that. Let's get into it. Okay, EAS. By the way, you can provide reagents here. Okay, how do you accomplish each of these reactions? And you can fill those arrows in. General mechanism. Okay, we have the other handout. White. The handwritten stuff. General EAS mechanism. We know the general mechanism, then we can bring in the specifics for each specific reaction. Okay, ultimately the aromatic with the H is going to be replaced. We just talked about all that with an electrophile. I mean, general E+, not minus, or ammonia, because ammonia is that electrophile or nucleophile? It's neutral, but it's a neutral nucleophile. These things attack, these electrons, okay? Electrophiles can be neutral, but in terms of charge, they're always going to be plus. Electrophile will never be minus. What does an electrophile, what does that term mean, electrophile?
Lots of electrons.
It likes electrons. Well, is this going to like electrons?
No.
No, physics tells us that this is going to repel electrons. Minuses don't like minuses. Something that likes electrons. This is going to like electrons. So it needs electrons. It wants to go back to be neutral. And so it's an electrophile. And the electrons here are going to attack it. Now, a common example of electrophile is H+. And we attack the H+. The H+ is an electrophile. And the very first reaction we did in Organic 1, we're reacting with alkene with H+. And we said the electrophile is H+. So, by the way, I would always be looking at your old handouts to solidify your knowledge. Final exam is comprehensive. Okay? And each time you read back and review your material, it'll just kind of make more and more sense and become more and more solidified. Okay, so here it is. The electrophile replaces the H. We generate H+. So the H doesn't take electrons with it like it does with SN2. Because here, do we generate Br+ when we do this?
No. Or minus.
What do we generate here?
Minus.
Br-, because the bromine takes the electrons. See, here it's the opposite. Okay, let's get past the general. Let's get into it. How do we do this? Well, it's really not much. The first half is the same as an alkene reaction. Benzene does have 3 alkenes, and we know they're delocalized, etc. But it will still react as just one alkene, at least initially. Now, it's not as reactive as a regular alkene. So we may have to heat this longer and higher temperature or provide a catalyst, but it still will do it. We'll talk more about reactivity, but we're just going to react here. This reacts with the electrophile, and we make bond, okay? Where are you going to leave cation at? That's my terminology for organic 1. Top or bottom?
Either.
Either is symmetrical here, it doesn't matter. Okay? Later it will. I added it at the top, so I swung my electrons out like this, right? Remember that? Swing it out, make bond, leaving cation here. Okay, I don't know how you guys did in organic 1, but this is some of the terminology I use with alkenes. Okay? That would give this new bond to the electrophile. Here. Now, this carbon is now sp3 because it has 4 bonds. This cation is often called a sigma complex because we just made a sigma bond to the electrophile. This intermediate is not aromatic because that carbon is now sp3 and does not have a p orbital. So the ring is not fully cyclic conjugated. The cation we made, though, is resonance stabilized. You should be able to draw resonance structures. Windshield wiper over, windshield wiper, okay? Resonance structures here. We'll be doing that plenty. Not going to do that now. That looks just like organic 1 alkene chemistry. Here's the difference. In organic 1, nucleophile that came in and added to cation, and we got an overall addition reaction. And the pi bond was gone. Here, and that would be addition, that's here. Okay? What does that be?
Base.
The what?
Base. Or nucleophile.
Okay, I'm showing a base. I would probably today call that maybe nucleophile, because I sort of tried to distinguish between base and nucleophile a good bit. Well, it's because it's mixed here. If it takes the H, it's a base. Okay? If it takes the H, it's a base. If it adds here, we call it a nucleophile, but I kept it B. Okay. But instead of the base added here to get an overall addition, where we add BE addition, instead something takes the H. And we call it a base if it takes the H. Then the 2 electrons from that bond fall in to make the pi bond again. Okay, if you can follow the electron movement here, you see that. But this is H plus because when we take H's, it's H plus because we're not taking the electrons. Now the base now is bonded to the H plus. But essentially, the H is lost as H plus, as an acid H. So in that regard, it doesn't look like a leading group at all. But it is now gone. Now this is sort of called a beta elimination. It's reminiscent of like the second step of an E1 elimination. Question maybe become, why does it even do an addition? If this was a regular alkene, it would do an addition. And we talked about how because you're making 2 new sigma bonds in place of the pi bond. And making 2 new sigma bonds is more thermodynamically favorable. But here, the more favorable outcome is to eliminate, you take the H. Why is that more favorable?
You said the higher energy state with the 2 pi bonds instead of 3 is a lot higher, so it's not as reasonable.
I'm not quite following you. This is not as reasonable.
Or no, that's
No, it is. This is better. Why is this better?
It has a lower energy state overall.
Yeah, why?
It's aromatic.
Because they're aromatic.
Yeah.
We restore the aromaticity by taking the H and doing that mechanistic step. We restore the aromaticity, and that's favorable. The outcome is not to destroy the aromaticity. This is not the outcome here. I wish I'd actually drawn this up here because this is higher in energy than that. It looks like I'm going downhill here. We react to give a sigma complex, then we take the H to put the electrons back in as a pi bond to restore the aromaticity. Okay? This is an EAS mechanism. It's pretty darn straightforward if you just understand the fine details here. It's nothing overly. Important though is resonance structures. One important thing. Okay? Just showing it here, the old windshield wiper, yeah, move electrons over, cation, electrons down, cation. Okay? Of course, the resonance hybrid. We can draw partial bonds all the way through here, and the partial charge is delocalized all the way through here. But not that carbon. That carbon is not part of the delocalization or the resonance, because that carbon doesn't have a p orbital at this point. sp3. Okay. So it's not aromatic cation, but it is lots of delocalization for the cation. This is the thermodynamics down here, which we alluded to up there. We make the sigma complex. That is your rate determining state or step. Okay, making carbocation. In fact, that's what we did. The sigma complex is a carbocation, right? From there, we can have two possible outcomes. We can remove the beta, do a beta elimination. Remove the H to go aromatic, or something can add to the cation, and that's an overall substitution. Overall addition. This is a substitution because essentially the H has been replaced by the E. Here, nothing's been replaced. We've just added. But that product is not as good as this product because that's not aromatic. Since it's higher in energy, the transition state leading to it is going to be higher. So which way is it going to go? This way. Water doesn't run uphill. Okay. Energy flows down here. Lowest path of resistance. Path of least resistance. Right? Question.
Is the product usually at a lower energy state than the initial benzene, or is that just a way that you just drew it?
Did I draw it same or lower to you?
You drew it lower to me.
Yeah, I don't. That's not a huge. There's not a huge difference there usually.
Okay.
I'm tempted to say, yeah, it's often lower, but no. Not significant. It's not a clear distinction here. Not to be. Where other reactions, yeah. For example, here, this is lower energy than starting because we have two sigma bonds compared to one pi bond. Okay? And this is what happens with alkenes. We get addition. You also get back bonding there. Remember back bonding? Okay? Back bonding is less likely up here because the cation is so resonance stabilized. Okay, that's general EAS mechanism. We'll look at specifics for each type of reaction, each type of EAS. First, halogenation. Now the report, which will remain due on Monday, does ask you to include mechanism for the halogenation. Okay? All right. Well, according to this EAS, the outline is there. Basically, instead of E+, we want to start bringing in specific electrophiles. right? Now, it's not always going to be E+. For example, with bromination, we're not going to form Br+. At least not just not a single bromine atom plus. Now for iodine, maybe. Okay. We're going to use chlorine or bromine. They're electrophilic enough. But we're going to usually need a Lewis acid. Okay. Common Lewis acids are iron salts, like FeBr3, or aluminum salts, like AlBr3 or AlCl3. Okay? These are very common. And this is a catalyst here. We have bromine. Now, if this was a regular alkene, it would react with bromine. You would not need a catalyst. You did an alkene bromination organic 1. It reacted instantly. Almost like a titration. This is less reactive because the electrons are delocalized. They're busy doing resonance. Okay? They still will react, particularly here if you add a catalyst. Roll with the catalyst. These transition metals tend to have empty d orbitals. And so the transition metals tend to be electrophilic. And what happens here is bromine lone pair will coordinate with the Lewis acid. And that's going to lead to this now bonding to the iron. Okay? Nothing new here. One lone pair. Now, we made this bond here. What's the charge of the bromine now?
Plus.
Bromine is now positive, and charge of the iron. Well, there's two ways to know that. You should already know the charge of the iron. What's the charge of the iron?
Usually it's plus 3.
If two neutrals react, the outcome has to be neutral. What's the charge of the iron? Minus. You can't create charge from no charge. Hopefully you learned that in physics. Two neutrals react, you're going to make a neutral. Yeah, two neutrals react to make a neutral. There's got to be a net neutral here. If two neutral things react and all of a sudden become positively charged, you have Nobel Prize. Okay? Two neutrals react. How else do we know it's iron? Because if you count electrons, the iron owns one of each bond. So it's neutral FeBr3, but now it has another bond and it owns one more electron. And if it owns one more electron, it must go from neutral to minus. Okay, here we go. But, see, does this have a dipole? No, but you remember in organic 1 we said it's schizophrenic and develops sort of a temporary dipole? Okay, and it's electrophilic, but it's like, well, how is it electrophilic? Does it really polar? What about here? Does it have a dipole now?
Yes.
See, now, this bromine is mad. I don't like being plus. I don't know why I bonded to you, iron. There must have been some reason. I liked you so much, but it got me in trouble. Okay? All right? Now I'm going to make your life miserable, and I'm going to pull on you because I want electrons back. And the pulling there makes this become lots of partial positive. And actually, these electrons see what's going on here, and they attack the bromine and kick this one off. And that leads to chemistry with the aromatic. I'm coming down here. That's looks like a equilibrium. It's two separate arrows. Okay. This is coming down to react there. Make bond to bromine. Nothing changed here. What's now at this carbon?
Carbocation.
Electrons came down. We have carbocation here. Plus what? Bromine, FeBr3. That's minus. This bromine got its lone pair back, neutral. Of course, our charge is balancing now. It's always going to be net neutral. But then here's our sigma complex. We've just added Br instead of E. We added E on the front page. Complexation of the bromine with the Lewis acid. By the way, why do we call it Lewis acid? What's the definition of Lewis acid?
Yeah.
Accepts an electron pair. What electron pair did the iron accept? The lone pair from the bromine. And aluminum can do this as well. Lots of transition metals, because they have there's empty d orbitals on these transition metals that these lone pairs can come in and fill. Okay, resonance. There's resonance there, right? Showed you on the previous page. You got to practice your resonance. Eventually, we'll have other groups here on the ring. We'll give you a chance to do additional resonance. Okay? This is our rate determining step, correct? It's all on the previous page. Just doing specific here.
Does that mean for simplicity's sake we can just show? Does that mean for simplicity's sake we have to show? We can just show the substitution with this upcoming lab report due Monday, because there are more groups that could do resonance, could there, or not?
It all depends on if you're asked to show resonance or if you're showing resonance.
Okay.
Okay. All right. I'm not going to show resonance here. It's on the previous page, and there's no resonance with the bromine. So what's our next step? Well, you got to recognize there's an H here. There's an H on every carbon. It's still there. What's the second and final step of the EAS mechanism? Okay, which means what? Something takes the H. Take the H, and then we're going to have the electrophile on the carbon instead of the H. All right, what can take the H? This guy, the iron's like, see, you can't keep these atoms happy. The iron's like, I don't want to be minus. I'd rather go back neutral. What happens here, and it's often shown this way, is the sigma bond here actually leaves the iron, and these electrons. Now, it may be the lone pair sort of does it, but often books will show these electrons breaking away from the iron and coming and taking the H, and these electrons coming here, and what does this all give? What does that electron movement give? It gives that. Now my ring is rotated. Obviously this carbon, yeah? It's turned a little bit. What else are we making here, though? HBr. What else are we making?
The catalyst reforms.
FeBr3. Because when this leaves that, that's just FeBr3. And what is this called?
Catalyst.
Yeah, we reform our catalyst. But we do generate HBr. That's the fate of the H and the other bromine. See, without the FeBr3, bromine reacts very slowly with Br2. Just not reactive enough. The Br3 allows for this complex to form and it makes it more electrophilic. Now again, did we ever form just simply Br plus here? We actually had a positive bromine, but it was actually not the one that got attacked. So we never really formed just that. And that's what most of these reactions are about. We got to understand what is the specific species we're forming that acts as the electrophile. Okay? You can do this reaction the same exact way with chlorine. Usually, you don't want to scramble your halogens, though. If you're doing Cl2, you'd want to use FeCl3. Keep your halogens consistent. But with chlorine, it's actually very common to use AlCl3. Because aluminum trichloride tends to be your most common chlorine Lewis acid. Where AlBr3 is never seen around. You never see that in the lab. Question?
Why don't you want to mix your halogens?
I can't hear you.
Why wouldn't you want to mix the halogens?
Do you have a particular reason for asking other than,
Just curious.
well, you don't want to end up with the other halogen on the, you're trying to brominate, you don't want to end up with chlorine on the ring.
So if you had FeCl3, it's possible that the Cl would have gotten attached to the ring?
Well, that's what I wanted you to ask. Why are you asking? Do you see a reason to be concerned? And the reason for being concerned may actually not really be there. So that's why I want to know, why are you really asking? It's just, it would look odd. It's like,
It doesn't
you're doing
sound like
bromination,
that.
but you're using aluminum chlorine. Because this, I mean, it actually could be, you have to think about it. AlCl3, can this lead to chlorine somehow? Is this chemistry known? If it is, it's going to cause you problems, because then you, okay. The safe thing is just don't mix your halogens, then you don't have to worry about this at all, whether it occurs or not. So, all I'm saying is typically you're going to have consistency here between which halogen and which Lewis acid you're using. Okay. Now actually, we can actually just use iron as a catalyst, or aluminum. That's because the base metal will react with your halogen to form your Lewis acid. And this would actually be called a pre-catalyst. It's not the actual catalyst, but it forms the actual catalyst in situ, or in the reaction. And that's actually kind of common because this can be unstable and hard to store, etc. It can also be hygroscopic, which means what? Reacts with water in the atmosphere, so it's hard to store. Why reacting with water? Because water has lone pairs, and these can add to the iron, just like the bromine can. But iron metal, on the other hand, is much easier to store as long as, well, it can rust. If you keep it dry, that's not going to happen that easily. Okay? So a lot of times it's, and in the old days, you see some old procedures, they'll add in like a piece of a nail. Okay? The nail contains iron. And so understanding how your catalyst can be generated. Question?
Why wouldn't, or what would happen to the H in that case to use the metal and not the Br2?
What do you mean, what would happen? You just create the FeBr3 and then you do the same mechanism.
Oh, you're doing that before you add.
Well, it's all together. I mean, you can take bromine and just add in iron. But before anything happens, these are going to react to make FeBr3, and then all this can happen. You will consume some of your bromine.
So what happens to the H then, if there's no bromine?
To what H?
H on the aromatic ring.
No, you gotta have bromine.
I don't know, if one bromine is attaching to the ring and one bromine is attaching to the metal. No, never mind, I got it.
No, it's all there. It's the same next time. We're out of time, guys. Question?
In the iodination, like lab, what specifically is the base that's taking the H?
You just say water.
Okay,
This is very weak bases. These are not strong bases.
okay.
Taking this H is like the second step of a E1. Like sulfate anion and taking the H.
Okay.
You're under acidic conditions there. Or water. Water can take the H and you generate H3O+. Got to be a weak base.